when we started talking about electricity, then we had talked about two charges, Q1, Q2, and they exerted a force either towards or away from each other. And so we developed the idea of this force between the two. And then from that, we came up with the idea of an electric field. So for some distance r away from a charge, then the electric field was given by some constant times q over r squared. Now, if we want to make that a vector, then what we do is introduce the idea of the r unit vector, so that if q is positive, it points away from that charge. If q is negative, it points towards, the r vector being a vector going towards or away from the charge. So that introduces us to the idea here of electric fields. The next question, what about magnetic fields? So we know that a moving electric charge, if it's in the presence of a magnetic field, it has a force acting on it. Okay, so the force would be perpendicular to both the field and the charge. So in the case that I've drawn here, V cross B, okay, so V cross B would mean the force is actually going to be into the page or into the screen. Okay, now this gives rise to the idea then of, well, what, because we know that if we have a charge here, okay, and we have a charge and an electric field, there's a force acting on it, and the force is directly proportionate to the force is equal to Q times E. So we wonder over here, well, would the force be proportionate to the moving charge? Well, what's the moving charge? Well, the moving charge is related to Q and to velocity. And so that turns out to be a little more complicated. In fact, it turns out to be very interesting how this works. Okay, so we know that this is going to be QV cross B. Okay, but now we work backwards. And we say, okay, so let's work backwards. And let's say that an electric field exerts a force here, so that means this charge produces an electric field. That means the moving charge is now going to produce a magnetic field. So we want to know, what's the magnetic field of a moving charge? Okay. So presumably there's going to be some magnetic field over here. Okay, and so we want to know, what is that magnetic field, and so what direction is the magnetic field, and so forth. Okay, now at this point it becomes very complicated, because what happens is that we know that if the magnetic field is this way, if the velocity is towards or away, there's no force. If the velocity is this way, there's a force, velocity that way, another force, velocity into the page and out of the page would also have forces. Okay, so that would suggest there's some sort of perpendicularness to this. Okay, well, that would suggest the magnetic field be perpendicular to the motion. Well, the problem is that if you're over here moving or over here moving, that if you have an r vector right there, some component of that motion is in the direction there and some component is perpendicular. Whereas up here, all the motion's perpendicular. And so that means finding the magnetic field of an isolated charge moving turns out to be very complicated. In fact, it's so complicated it's beyond the level of this class. So instead, what we're going to do is we're going to say, well, let's imagine we have a wire, and the wire has current running down it. Okay, so the current running down the wire has charges here, 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 here. So if I'm looking for what's the magnetic field out here, then what's happening at the ends here are kind of balancing each other. And so it doesn't really matter. We can find the magnetic field due to that current. So that turns out to be much simpler, and that's the approach we're going to take. So the problem here is that the magnetic field does depend a little bit on, where you are along here. So we can talk about some little a bit of dq or derivative of the current right here. And so what we normally do is we say that we are going to define a differential magnetic field due to this little piece right here. Now, we don't really have dq here, but we're going to have I times ds. Okay, so remember I is dq dt. Okay, so I ds is going to be basically dq ds dt, or in other words, dq times v. Okay, and we know the velocity is what's important in the magnetic field right there. Okay. Now, so that's going to be my dqv. Okay, and the magnetic field is going to be perpendicular to the line here that this is moving and the distance right there. So that means that the magnetic field is going to be perpendicular to that. Well, to get perpendicular, what we would do is do IDS, because we'll say we're defining some little ds right here. The ds is going to be like a dx in the direction of the current cross r hat, where r hat is a unit vector pointing in that direction right there. Just like with the electric field, which is inversely proportionate to r squared, this is going to be inversely proportionate to r squared. And so the magnetic field is going to be here, and we're going to have some sort of magnetic constant in here. So we can say some magnetic constant times I ds cross r hat over r squared. Okay. Now, this magnetic constant you almost never see. In fact, it's virtually never written out anywhere. And that's because in most equations other than this particular relationship, right? Sorry, this is dB. In most other relationships here, then rather than seeing that, what we do is we end up with 4 pi k sub b. And so we give that a name, mu naught, which is the permeability of free space. Okay. Mu naught turns out to be equal to 4 pi times 10 to the minus 7 it's Weber per am meter, okay, or that's 4 pi times 10 to the minus 7 Tesla meter per amp. Now we'll explain what a Weber is later, okay, but a Weber is equal to a Tesla times meter squared, and we'll explain why that's the case later on. So, since we now almost never see k sub b, we see the mu naught, k sub b turns out to be equal to mu naught over 4 pi. And so we can then put all this together. So this differential magnetic field is mu naught over 4 pi times I ds cross r hat over r squared. And so that is called the law of Biot and Savart, after two physicists that studied this. And so the Biot and Savart law is how you actually find the magnetic field. You find the differential magnetic field due to some little piece right there. If you want to find the total magnetic field, the total magnetic field would be the integral of that. So the total magnetic field would be the integral, the mu naught I over 4 pi all comes out, and so that's the integral of ds cross r hat over r squared. Okay, and that would give you the total magnetic field. Okay, so that's how you'd find it.